All right, so this video is going to be on electrophilic aromatic substitution. As shown, you can see the benzene basically adds an electrophile to its ring and you lose a hydrogen, okay, or an H+. And that's kind of one of the few reactions that benzene will do because it's so stable, right? It's not, it's pretty similar to when we have, let's say, an alkene and we attack an electrophile with that nucleophilic alkene. You form a carbocation and a new, basically an added product. It's similar, but it's going to be a little bit different from this point on. Okay, and as you can see, it's not. This would be an addition reaction, whereas the benzene is a substitution reaction. Okay, so electrophilic aromatic substitution. Okay, so let's take a look at benzene, the mechanism more in depth. So let's say we use the pi bond to attack that electrophile, as you saw above in the alkene. We would still get a very similar intermediate. So we still have that electrophile there. We have the hydrogen that was there originally, and then I'm going to draw this extra hydrogen just for clarity, so we can identify that it's clearly a carbocation intermediate. Okay, so there's three things on it. All right, so here's the thing. This is not very happy right here because this intermediate is not only a carbocation, so it's high in energy, but the activation energy to achieve this process is even higher than the alkene because we've interrupted the stability or the aromaticity and the stability that it kind of contributes to that ring. And so since we've kind of ruined that, then we had to overcome an even higher energy barrier. And so activation energy is much higher for reactions with benzene than it is with typical alkenes for that very reason, because the intermediate is no longer aromatic. In fact, the carbon with the new electrophile on it and the intermediate is actually sp3 hybridized. So there's not even resonance stabilization that can occur. There is with the cation and the other two pi bonds, though. Okay, but that's neither here nor there. We can continue on with kind of a description of the more or less five different. I'll give you an extra one, but 5 different reactions with benzene. Okay, and so the first one is going to be halogenation. So we're going to have, I drew one hydrogen explicitly because we're showing that we're substituting that hydrogen with an X atom, where X is chlorine or bromine. Okay. We also have a nitration reaction. So nitration is when we have a benzene ring again, and we substitute that hydrogen for an NO2, a nitro group. Okay. We have sulfonation, which is a very similar process to nitration, and we have where the benzene ring hydrogen is substituted with a sulfonyl group. So we have an SO3H group. All right, so the fourth one is when we have, these are some fancy ones. They're called Friedel-Crafts, and then the first one we'll discuss is alkylation, and then another one after that is Friedel-Crafts acylation. Okay, so the Friedel-Crafts alkylation is when we substitute a hydrogen atom on the benzene ring with an alkyl group. Okay, fair enough. Friedel-Crafts just is basically the chemists that discovered this and kind of advanced this particular reaction. The Friedel-Crafts reactions are also really, really helpful because they actually create carbon-carbon bonds. And so anytime you can make carbon-carbon bonds, that's amazing because synthetic chemists are always trying to make new products, okay? So the Friedel-Crafts acylation substitutes that hydrogen for a carbonyl group, okay? Specifically, it's going to make a new ketone, okay? So let's go over the general mechanism. So the general mechanism is going to help us really understand how all of them work. There are going to be some generic processes, and then there will be subtle, unique processes for each individual reaction, but more or less the process is the same. Okay, and we have a benzene ring with an electrophile. I've highlighted in blue. just because I like when the electrophile is blue, it's like it's cool and cold and not very reactive, but or it's just chilling, right? Really, the nucleophile I like to draw in red. That's the benzene ring, and that's the thing that does the attacking usually, right? So draw these in red. It attacks that electrophile, and then it eventually gets rid of that hydrogen atom, or the hydrogen, the H plus, the proton, to give you a substitution product. Okay, so let's take a look at the mechanism to see how that hydrogen leaves. So we have our benzene, and it attacks the electrophile. What would form next? We have still the 2 pi bonds on the bottom are not touched. We have the carbocation intermediate. You've already seen this already, and we have our electrophile on there. Trying to keep the color coding similar so that way you can follow the electron flow, but I might eventually ditch that because it is tedious switching colors. But remember, this is a high energy species. It's a carbocation. It's no longer aromatic, so it's pissed. But it is resonance stabilized. It's almost like an allylic carbocation, right? So a base would come along, remove that proton to reestablish aromaticity. So this is a highly favorable process. Very easy to do, reestablishing that aromaticity, and then also you can see that new electrophile is on there. So it's called electrophilic aromatic substitution because we removed an H+, which is an electrophile, and we replaced it with another electrophile. Okay? And that base can be a variety of things, and that might vary from mechanism to mechanism, as well as obviously that E. But the first step where the benzene attacks the electrophile of some sort and forms that carbocation intermediate followed by deprotonation, that's all the same. We just got to figure out what E is, okay? So halogenation, we've got the substitution for a halogen, right, where it's chlorine or bromine. It's not going to be iodine or fluorine because iodine's lame and it's too slow, and then fluorine is too reactive, it's violent, okay? Here's the kicker for halogenation. It's really all of these electrophilic aromatic substitution reactions, we need a Lewis acid, okay? So we need something to make this, because I did mention that the activation energy is really high to overcome that barrier. We need to add a Lewis acid, okay? So this kind of supplements the reaction to move it forward because we need to overcome that high activation energy, which ruins the aromaticity of that stable benzene compound. Okay, so in the case for halogenation, it's usually like iron with whatever, like an iron tribromide or trichloride. And this, if you're using chlorine to substitute, then you want to use the iron trichloride. So the chlorine, elemental chlorine, kind of attacks that Lewis acid iron center, and then you make this Lewis acid base adduct, shown here with the positive chlorine and the negative iron. And obviously that chlorine doesn't like to be positive, so it's going to kind of take a little bit of electron density from the adjacent chlorine. They're going to share because they're friends, they're best friends from the beginning till the end. So that makes that chlorine, that terminal chlorine, more susceptible to nucleophilic attack by the benzene ring. So that's actually our electrophile. That's our E plus right there, that delta positive chlorine on the end, okay? So once I've attacked that, it kicks the electrons to the positive chlorine and makes it happy again, right? And then we got our typical intermediate with our positive ring, positively charged ring with the electrophile now on there, okay? So we do have that iron complex, that anionic iron complex floating around, and that's basically the source of our base. So let me move this guy around. He can grab on that proton to reestablish aromaticity, and so of course we're going to get our substitution product with the chlorine on there. Sorry, there we go. Kind of wanted to keep that bond red again just to show you. Not only did we form that substitution product, but we've reformed the iron trichloride and as well as HCl. Okay, so the iron trichloride can go ahead and come back and do that job again. So we don't need to add the acid catalyst in stoichiometric amounts. It can be a little bit less than that. Okay. All right. So that's pretty much the halogenation process. I just wanted to introduce you to the general mechanism and then throw that one mechanism at you for halogenation. Again, it's going to be the same process for bromine and generally the same process for all of the electrophilic aromatic substitution reactions. And so in the next video, we'll go over more of those reactions in pretty quickly. But before I do that, I want to leave you with a couple compounds here that are, as you can see, have benzene rings with chlorines on them. So this is Wellbutrin, and then on the right it's an antihistamine. And so halogenated benzene rings, first of all, are like super pervasive in pharmaceuticals, and then halogenated compounds are as well. So just wanted to bring that up because this is extremely relevant and a very important reaction. Okay. Let's take a look at these guys though. So these are more infamous and unfortunate because the structures are interesting, right? They do have halogenated benzene rings on there, but these two components are basically the ingredients to Agent Orange, which was a chemical used in Vietnam and has been associated with a lot of adverse effects for those that fought in Vietnam. So, but yeah, anyway, the structure, right? So that's halogenation in a nutshell, as well as our intro to EAS, electrophilic aromatic substitution. Yeah.